been hit by a rogue skateboard that lost its rider? Maybe you've been the one chasing the skateboard because you jumped off in order to avoid an accident. If you ask any skateboarder, they'll tell you that this is a pretty frequent occurrence for them. And because UCSB has a large population of skateboarders, this is a common occurrence on campus. Not only can this hurt pedestrians, but this can cause damage to the board if it hits a wall. We aim to fix that problem.
So for our projects, a skateboard with an automatic braking system, we ended up choosing two different benchmarks to compare our product to because we couldn't find any single competitor that was a direct competitor to our project. The benchmarks we ended up choosing was a skateboard with a manual braking system and a scooter where you apply pressure to the back part of the scooter to create torque that causes braking. For a skateboard with manual braking systems, the benchmarks we used to compare to test our product included features such as aesthetic design, how unnoticeable the braking system is, and ease of use of the braking system. It was how far you have to stick your foot down and how much pressure you have to apply that we used for the benchmark system.
When it came time to build the prototype, we started off with a works-like model that consisted of two 3D printed brake levers, a spring, two pulleys, a cable on a wooden block. And if that worked, then we were going to go ahead and machine the parts out of aluminum to keep the weight down.
From the works-like model, we were able to conclude that the full-size model of the levers would be rigid enough to work as part of the prototype, and we would avoid the need to machine. So we decided to just go ahead and 3D print the brake levers for the final prototype. This part could be manufactured commercially given the convenience and ease of 3D printing. When testing the works-like model, we were able to see challenges that we had not thought of when working with a CAD model, such as the position of the pulleys in order to have a maximum range of motion of the levers to disengage the brake while riding. We had two main engineering characteristics: the distance to stop and the time to stop. The benchmark for the distance to stop was 30 feet, and our target specification was less than 15 feet. From the final prototype testing, we were able to see that we actually stopped in less than 3 feet. The time required to stop, the benchmark for that was 3.65 seconds, and our target specification was less than 2 seconds, and from the prototype testing, we got it down to 1.6 seconds, so we did exceed our target specifications.
Our design goal was to have a skateboard that stopped when the rider comes off it and not while the rider is on. So we were kind of concerned with how we engage the brakes, so we came up with this push plate that engages the brakes while the rider is off and not on, which is backwards what it usually does. So we had goals of having it stop 15 feet prior or after the rider comes off. We reached that. We had goals of stopping in about 1.5 seconds after a rider comes off. We reached that. We had a goal of having it be less than 5% of the total weight of the board. We did well with that. And wait, hold on. Did I mention it stops?
The hardest part of this entire project was deciding between a purely mechanical system and an electrical mechanical system. We went for a purely mechanical system due to time constraints, but we planned on going to an electrical mechanical system. That is because with a mechanical system, we not only have a pressure plate, but we have tons of wires which you need to drill into the board, which you hook up to your actual brake system. Instead, what we would do would have pressure plates, which would sense when you're off the board. This in turn lets us set a time delay to the Arduino, which could be set to actuators to stop the board instead.
So initially, our design was inspired by push rod mechanism, which is often used in Formula One suspension setup, as you can see in the diagram. The idea is to transform the vertical force in the vertical plane onto a somewhat horizontal plane for better, more compact designs.